Okay, everybody, let's get started. So we're going to have a lecture today on interconnect, but I still have to finish up a little bit of the last lecture on the devices and delay. But I wanted to start out with my slide. Okay, I did go over homework 2. Everyone has gotten a grade. And again, it's completion-based. Some people did not complete the homework. I emailed a number of people I'm concerned about. If you got an email, feel free to talk to me. I'm surprised that people didn't have answers for some of the problems entirely. That's pretty bad. The rest of the people I went through, and I think I have mixed. I'm happy in some ways, and I'm sad in others. I'm happy because I see a lot of mistakes. They don't make me happy, but these are mistakes that people usually make on the exams. Okay, the mistakes I do see are things that people always don't fix and then have problems on the exam. So now's your chance to go look at our solutions and figure out what you did wrong and reevaluate your homework. So I think from that perspective, the homework being completion-based is actually working on my side. If you go back and look at the solutions and see what you did wrong. So there's this next step of that you have to do to help you do well on the exam. And yeah, it looks like most people worked fairly independently and tried to do it as they did, which I'm happy about that. So I'm not going to say much more about the exam, but I'm going to remind every time that the first midterm is not this Thursday, next Thursday, the 5th in class. I am going to announce that we'll have 2 rooms. I'm going to move half the people to another room so we can spread out. So yeah.
Can I ask if, like, the midterm is like multiple choice?
I'm not going to go over the midterm. It's a variety of formats similar to your homework. But you can expect stuff like that. Yeah. As I mentioned last time. I talked about last lecture, actually. So yeah. You need to know everything I talked about in class and everything in the homeworks. So everything's fair game. But Ali earlier asked, is it memory-based or learning-based? I'm not going to ask you syntax of SPICE commands. I don't care about that. What they do, maybe. Like how they behave. Yeah, like the homework. So I think that's the key. I want you to understand most of the stuff I talked about in lecture and then what applies to that. So, and again, you can use an 8.5 by 11 sheet of handwritten notes. So you can start out, if you want to remind yourself what specific SPICE commands are, you can write them and make notes. Just no printing at all. So even if you write on an iPad, you can't print your iPad results because you can shrink it down. So handwritten with a pen or pencil. So that's the rule. All right. Yeah, I've had people do that. Oh, it's handwritten, but I zoom my iPad down to this big, and that doesn't fly. So okay, you see everything when you're in this job long enough. So okay, so we'll talk a little bit more about layout file formats. So we talked about the delay, measuring delay of CMOS gates, how to do that. What's it boiled down to? Everything is basically Elmore delay, and that's the thing you can do to approximate stuff to the first order. But when you actually use the tools read in file formats with the different data. Can you hold on with the chatting up front because it broadcasts up here? The file formats contain different information depending on what the tools are doing. For example, for layout, the actual physical mask generation, there's 2 primary file formats. You've already seen one in the tutorials, the GDS or GDS2. This is basically a full layout information. So it has all the layers, kind of the numbers, and it doesn't have, as I mentioned early on, the color patterns and things like that. That's in your design kit that you can look at. Now, that has a lot of information that's not necessary for a lot of the steps. When we start getting into placement and routing, which we'll do after in quite a while, like another third through the quarter, you end up wanting a more abstract layout format, which is called LEF, or this is layout exchange format, LEF. There's also a DEF, design exchange format, but LEF is in particular used for the library cells. And this used to be a format by Cadence Design Systems. They're one of the major 3 EDA vendors, but they basically, I don't know if they officially open sourced it, but there was a spec, maybe through IEEE, and most tools can read this in and out. So these are standard formats used by most ASIC tools. The nice thing about this LEF is it abstracts away basically the devices of your design. Like if you look at this is a cell captured from a layout tool. I don't know what cell it is, but you notice all it has is the metal, and it has pins. You can see some faint pins in this thing too, right? You can see maybe a pin over here and a pin over here, maybe. The idea is that if we designed our cells correctly, like we talked about last time, where you have these half a DRC on all sides, you don't need to know the contents. You can throw away this actual CMOS transistor and transistors and say, I just need to know it's a box, it has this logical function, and where to connect to it. And so the place and route tools use this for doing design. And if you go into the place and route tool, you can't turn on the transistors because it doesn't even have them in memory. And it does that because it's a lot of extra data that would slow it down. We end up running designs that are hundreds of millions of gates, and you have giant servers with half a terabyte of memory, and you're still running out of memory because of the design size. So there's no reason to include this stuff. Now, yeah, so basically the pins, metal blockage, and power rails. Now, what else about this? That's primarily the main stuff about this file format. Now, you may say, okay, well, this tool uses this file format. How do I get back all of my transistor information? Well, usually there's a step at the end. It's kind of it's an unwritten step. It's not in most methodologies. It's basically called streaming out. And what this means is you basically have GDS files of your lib cells, and then you end up having your design, and you add these together, and then these basically output another GDS file. And so this LEF file is going to have all your library cells that you then place, and they have locations, you're going to have wires that hook everything up, and that's actually in that def file that I mentioned. That kind of goes along with the LEF file. That has your design information, and so you basically have the GDS of the library, the def file, which uses these LEF cells, and you basically substitute everything. If you placed an inverter and you had a LEF of an inverter, you say, oh, grab the full GDS, put it in that place with the correct orientation and everything. So if it's flipped, and so on, and have the wires connecting it up, and output that to another GDS file, which you essentially merge them together, and then you send that one to your fab. And so that's how you can abstract away this during your placement and routing phase of design. And later when we learn about this stuff, you're going to see some of these designs at different stages, and you're going to look and debug stuff with a view of a design with LEF files. So again, you don't even need to know the transistor stuff at that point. Now, that's physical design of the masks, right? Now, the other very, very important thing is, so that's connecting everything up, making sure it's logically correct, and so on. The next thing is determining what is the speed of my design, does it work at that speed, and what's the power consumption. We're going to talk about this after another 2 lectures, for at least 2 lectures also, on an entire thing called static timing analysis. This is how you analyze the timing and the power of your design. But you need inputs to that tool. And what are those inputs? Well, you have to have what's called a Liberty file. I think it's actually I don't know if it was always called Liberty, it was called .lib, and I think it was originally a library file. But this was actually a file format that was then open sourced by Synopsys, another one of the EDA companies, and they said, oh, everyone can use this format. And then they called it Liberty, right? Oh, it's free. But there's it's actually a very complex syntax for this library file, but I'm going to show you a few of the things because you can get information about your design cells through it. And obviously I don't expect you to know the exact syntax, but it contains a lot of the information you're going to use for your design. Now, this Liberty file, it's going to also have a number of different Liberty files, and all of them refer to the same set of library cells, okay? And what we end up having is what's called a corner. So these things together determine what's called a corner. Now, what I mean a corner, it's a set of extreme values of operation. And we include what's called a process parameter, a voltage parameter, and a temperature parameter. So, and what this is supposed to do is when you're operating your chip, you're going to be running it at, say, some temperature. If it's a summer day in the back of your car, it's going to be closer to like, maybe not 80, maybe like high 40s, right? But if you have a bad heat sink, it might be 100 C. Voltage is going to depend on your power source. If your battery's dying and the things may lower the voltage, you may have a lower voltage. You may have a difference in a power supply. Every power supply is going to be plus or minus 10%. You may have gotten a good one or a bad one. You want to make sure it works at all these kind of values in between. And then you also, the first one is the process parameters, which is the actual manufacturing. Every day a fab turns out chips, every batch of those chips, every week, every month, you're going to get different parameters that change. Like one day your transistors may be really fast. The next week you have a different engineer on the line and they're a little bit different. You may even have proximity effects. We talked about like CMP and things like this. You polish your chip. It may be on your same die. Some of them behave some way, some behave another way. So this is defining whether your transistors are fast, slow, or typical. And up here you see FF. This is typically for PMOS and NMOS, fast, or NMOS and PMOS. It depends how you label it. So this would be both of them fast, a high temperature, and this voltage. So 1.65 volts, for example. And they just do the V. They'll frequently do a V or a P instead of a decimal just because you like to have only a period for the suffix, right? Do you have a question up here?
Yeah, I was making sure that you meant like typical fast, slow as descriptors for NMOS or PMOS, not like slow NMOS specifically.
Yeah, no, it will mean, so if you have FF, I don't know the order, it might be fast NMOS and then you could have slow PMOS, FS. And what would happen when you have FS, for example? If your NMOS are fast, the pulling down transitions are extra fast because your NMOS are strong. But if your pull-ups are slow, your rising transitions are slower. That may change the behavior of your design. If you have a path that's really dominant on the PMOS pull-ups, that could fail, right? Or let's say you have a stage in your logic where you're pulling up in a huge fan out. That could be bad in that corner. Yeah, over here. TT is typical. That's basically you're assuming ideal NMOS and ideal PMOS. Now, kind of a preview. Why do you care about fast and slow? Well, slow makes sense, right? You have your critical path. What about fast? Hold time violations, exactly right. In most designs, you're actually more concerned about hold time violations than your slowest critical path. And we'll talk about this with static timing, but if a hold time fails, your chip is a brick, it doesn't work. If your critical path is slow, you can turn down the clock frequency and it should still work. So you can fix a setup time by just slowing everything down. So we'll talk about that a lot when we talk about static timing, but that's an important aspect of this, yeah.
So the FF part of the name is only typically a T, an F, or an S?
Yes, only a T and F or an S, that's correct. Yeah, typical, fast, or slow. And you'll see all these files in the process PDK directory. In the homework when you did SEAL and you kind of made you cloned everything to get the GS for your library of the cells you looked at, there's another directory called lib. That contains all these files. So the GS directory contained all the layout. There was a left directory that contained all the left files for the place and route tool. And there's a lib directory that has all of these. Way back in the corner over here.
If you have like a hold time, is it non-trivial? Does it add delay block?
That's a good question. How do you fix the hold times? We don't really talk about it too much, but yeah, you have to add delay. The trick to that is if you add delay, you can have paths that are on a hold time path in one part and a critical path in another part. So if you fix a hold time incorrectly, it may make your critical path slower. So it's not a simple problem of just adding delays in all cases. But the other thing is, if you're suddenly adding logic to slow signals down, that's bad, right? You're burning up power to make things slower, and you don't want to do that. So frequently, when we use STA, if you set up your constraints wrong, so what you're checking, the optimization tools will go through, and if you just set them incorrectly too much, they'll keep adding buffers until you run out of space. And your design will still not work, and it'll be full, and you can't route it, and you can't finish it. That's a very common thing if you are kind of setting things up incorrectly. Yeah.
Does EDA automate this, or you have to?
Does EDA automate this? That's a good question. Yes and no. I'll talk more about it in static timing, but generally, when you make sure your design works, you're going to have to make sure it works at a bunch of different corners. I'll talk more about it when I talk about static timing. Yeah.
So they provide files with sort of a lot of permutations or combinations of
Yeah,
these parameters?
yeah, different permutations of these. I forget in Skywater there's like 12 of them. They give you 12 corners. And what this means is, in terms of voltages, you might have like 3 different voltages. Well, what if you want to run your design at a speed that's not one of those voltages? No, it doesn't do it. Because you have to basically recharacterize your library with SPICE, get all of the impact on all the gates, because each gate could be affected differently, right? It's not a linear interpolation necessarily. Yeah, so the reason they don't do more is you basically, for every gate, you have to do every combination of all of these things, right? And we'll talk a little bit about more. Even measuring it for a single gate requires a lot of work. That's actually my next slide. Did you have another question? No. Okay. So what are in these Liberty files? So we now have one for each corner, right? Each operating condition, manufacturing condition. Well, there's generally 2 formats. In class, we primarily use this one, which is an older format. This is called a nonlinear delay model format, or NLDM. And basically what it is at a high level is you end up making a table of values with different input slews, so that the transition rate of the input signals and the output load capacitance. And you do this for every input of your gate. So if you have a 4-input gate, you're going to do A, B, C, D inputs. You're going to change the input slew a bunch of times, have a bunch of different loads, and run SPICE. And basically this table is frequently something around like a 6x6 or maybe an 8x8 table of input slews and output capacitances. Now, your question over here, can you interpolate stuff between the process corners? No. But here you can interpolate these. They basically have a table like this, and I'll show you on the next slide. But you can do interpolation. So I'll wait till the next slide to show you that. But ultimately, you're limited by the size of the tables. Now, there is another more recent file format. It's called current source models, and it's either CSM or CCS, depending on which EDA company uses it. And what they do here is instead of having basically an input transition time and the output load, you basically have an input voltage and an output voltage. And then you kind of measure the transition of this. You're basically going through a waveform on the input and computing the output voltage change for every change in the input voltage. It's kind of like a SPICE transient simulation, but it's a little bit more accurate, and you model this in terms of this behavior. The bad thing about this is created in the same way, a similar way. You're running a bunch of SPICE simulations, but the problem with this format is when you look at it, it's kind of meaningless. If you look at a particular entry in the cell, say for an inverter, it's going to give you a value of for the input and output voltage, but how fast is the gate? I don't know. In the NLDM one, you can look up in a table and say, how fast is this gate? Oh, it's 20 picoseconds. So it's kind of intuitive, and you can get the information. But it's less accurate. So the second one's good for accuracy. These library files also, or Liberty files, library files also include some other stuff about the cell area, cell function. So when you want to swap cells, can I substitute logically? And some other things. So that's all in this Liberty file. Now, what do I mean by the capacitive load and signal slew? So we already talked about this a little bit, right? Capacitive load, basically, if you have a fan out, it adds more capacitance because of the gates of the fan out. We talked about how to compute that last time. Also, longer wires add extra capacitive load. So this is all that adds to the load of the gate. And these all get summed up, right? You may have the gate cap here, the gate cap here, the gate cap here, along with some wire delays or wire caps. And you basically sum all of these up, and you end up with a load cap, CL. And this load cap gets used for figuring out what the delay is of this initial gate. And then we also have the input slew. Again, I'm using this interchangeably with rise transition or fall transition, but some people call it a slew. And usually this is the 10 to 90 or the 20 to 80 rising or the falling delay. Now, obviously the capacitive load changes your delay because the resistive output of a gate has to drive more capacitance, which takes more time, right? L more delay is R times C. Well, the input slew technically does too, because this determines how quickly the transistor turns on or off in your P and N pull-up networks. If you have a very slow transitioning input, there's going to be more time where both of those gates are on, and it effectively turns on slower. So slower slews mean slower delays. Sharper slews mean faster delays in general. Now, what do these nonlinear delay tables look like? Now, again, the CCS models have the same thing, except instead of input slew and output capacitance, it's input voltage, output, and output voltage. But they're very similar. Well, you end up having two tables for every gate. Actually, you have two tables for every input, cross product with every gate. Also for every rise or fall, right? Because a rising input is going to have a different delay than a falling input on a gate. The A input of a gate is going to be different than the B input of a gate. And obviously every gate, if I have a NAND, say, size 1, that's going to be different than a NAND size 2. And if I have a NOR versus NAND, obviously those are different functions, and so those have different delays too. This is a big cross product, right? Lots of different tables. But it can generally be kind of summarized into these two tables for each one of those. And for each of those, you then also have a number of different input slews. This would be all the rising input slews of a gate, and output capacitances, a range of output capacitance. And this may go from like, 1 fan out to like 8 fan out or more. Maybe even 16 fan out, a big load. And then what is the input slew? We're going to have something that's really sharp down here, and then something that's really slow. Maybe I have them backwards. They might be indexed the other way. And then what happens is you can basically say, when I run Spice, if I run Spice, let me flop them just for be a little OCD. The sharper one on the top, and this one down here. And let's say we want to run a simulation. We run a Spice simulation for a very fast input with 1 fan out. This is going to be kind of a really fast delay. Or we run it with a big fan out and a slow input signal. This is going to be a really slow delay. And you can kind of see there's going to be roughly a gradient kind of in this thing that goes over that range. Now, if you want to figure out a delay, you can say, okay, my input slew to this gate is about this. And if my load capacitance is about this, I can figure out the delay. Like let's say this one is 4 fan out 4. If I want to figure that out, it's going to be right down here in this cell with the slew of this. And part of your homework 3 is actually looking at this to figure out values for some gates. So I actually have you go in, trace it down, and then you're going to run Spice and see how close Spice is to it. Okay? So you're going to see the correspondence between it. Now, what happens if I'm, yeah, go ahead.
Sorry, I started homework 3. I was curious, is the rise delay almost like equivalent to like the fall delay?
Is the rise delay equivalent to the fall delay? The short answer is no. Absolutely not. The extreme reason, compare a NOR 3 and a NAND 3. NOR 3 has the 3 stack transistors in the pull-up, and a NAND 3 has the 3 stack transistors in the pull-down. So they're going to scale oppositely. But we usually try to size them to have a similar delay, right?
Like the numbers were pretty similar.
Yeah, because you basically size, when we had 3 pull-up transistors in NOR, we increased the size of the PMOS to compensate, right? But now what happens when we go back here? This is a good question if you dig into it. What if we go back here to these corners? How does the temperature affect that? Well, the temperature is going to probably affect the PMOS devices more than the NMOS devices, maybe, I'm guessing. What about if we're in a different corner? Let's say we're in the slow NMOS corner or the slow PMOS corner. That's going to change them a bit. You're going to have them skewed, right? Because you're not going to have the typical PMOS devices, and that NOR gate is going to get much worse than the NAND gate with the pull-up. So, and then also voltage. The voltage may affect them also. So once you start doing this, everything's affected a little bit differently, and so you'll get different results. Yeah, that's a good question when you dig into it. So. Now, what happens if you have a fan out that capacitance, that's not exactly 4, but it's like between 3 and 4 fan out? Well, you can interpolate. And what do I mean by interpolate? Well, let's say worst case, you might have to look at 4 cells here and figure out in 2 dimensions, you do a linear interpolation. You know how to do a linear interpolation in 1 dimension, right? If you have 2 points, you basically draw a line and you find out the value wherever in the middle. Well, now imagine you have a plane. So 2 dimensions, an x and a y with a z dimension that's delay. You just compute each of those independently. And worst case, you'll do this with 4 cells and compute the value that's somewhere between all of them. Yeah. Does the method of interpolation matter? I believe they all just do linear interpolation. Yeah, that's a good question. There's probably some options on the tools to interpolate differently. Because if you think about, this cell over here could affect a little bit going over here, like you want to be continuous, but I don't think they actually do that. I think it's pretty much just a linear interpolation. Yeah. No, that range. Yeah. This is another question of how many simulations you want to do in Spice, how accurate you want your models to be, and how big your files are. And so it's in that ballpark of 6x6, 8x8. That's about normal. I haven't seen much out of that range. Yeah. So one of these tables is going to be the delay. So I call this the delay, the intrinsic delay right here. Then we're going to have another table that instead of measuring the delay to the output, we're going to actually measure the slew to the output. So we have an input slew rate or signal transition, and then we're going to have an output transition as well. So if we run our Spice, let's say the input rises like this, and then the output goes like this, we literally measure the different transitions, so the 90 to 10. And we put that in the table here. Because when you have an incoming signal transition, if the output is, say, a big drive gate with a low fan out, it's going to make the signal crisper. It's going to make it more square-like. Where if you have a very big fan out, it's going to actually make the signal transition worse. Like it could become a problem eventually. And so this kind of lets you know not only the delay of the gate, but then what the output of the signal looks like going out of the gate. So you have a duplicate table which has all the values for those same input slew and output capacitance pairs, but instead of delay, it's the output slew rate. I'm going to skip over this one, but this is, again, the same idea with V and V out. Now, what if we look at this? Yeah. Let's go over here and then here. Not this one. Or do you want to look at this one? This one. So it's the 10 to 90, it's still time, but it's the 10% of VDD to 90% of VDD. Remember, way back here, it's this. So if your signal actually looks like something like this, you're going to approximate it like that kind of piecewise linear thing. That's different than the delay. The delay is going to be if the input is going like this and the output is like this. Last time I talked about the 50% delay. So this is the delay. Yeah. And I talked a little bit about that early on in last lecture, I believe it was. Yeah, that's why sometimes you need to re-review these because there's a ton of information in these lectures. I understand that. And that's why, asking when you're confused or going back and revisiting stuff can be important. I think I have some people that even have come to attend this class a second time just because they're like, oh, I missed stuff the first pass. They did well in the class, but they're like, I just want to revisit it again. So, and I also have lectures. Has anyone watched the lectures? Are they capturing good? Well, okay. I haven't actually viewed them myself. Yeah, it stops at a given time. I don't control that. So I ran long one day. The one day I went over 5 minutes, so that would probably cut off that day. What about the camera?
There is no camera, it doesn't matter too much, there's no draw.
Oh, it captures this. So yeah, I try not to point. So yeah, that's I'm trying to rid myself of that. My stick is still here, but I won't use the stick. Okay, good. I'm glad they're at least capturing. Now, if we look at these lib files, so they're text files. You can have compiled ones. They're sometimes called a .db. Again, database, I guess. This is a compiled lib file. I don't see these so often anymore, but if you make them as a binary file, they're going to read faster, right? Because parsing text can be slow. And again, these are big tables of numbers and all this stuff. But you can't look at the DB files. If you look at them, though, if you kind of do some searching, there's a few keywords in here that you can look for. Like you're going to see a cell keyword in all libs, and you're going to see a standard library cell name. Like here's an AND2 size 4. And some of the interesting stuff in here, you're going to see, this is the area of the cell. What are the units of area? Well, you have to look at the top of the lib file, and they're going to generally have a kind of a prelogue section that says, oh, area is in like micron square or something like that. It can be in different units in different libraries. And so this just says 359.1 units of area. I don't know what that is until I go back and look at it at the top of the file. And then you're going to have basically clauses for each pin. Here's a pin clause, another pin clause for the input pins. And you can see here for input pins, it specifies the direction, and then you have a capacitance. This is the gate capacitance of that pin, right? Sometimes you might have more than one capacitance. Like you could have a capacitance, and I believe they'll also have like a rising capacitance or a falling capacitance. Because remember, the thing I showed you about the gate cap is it kind of depends on the state of the transistors a little bit. So you can have a different value depending on what the states of the transistors are. And so you'll frequently have two values for this capacitance. Yeah.
Is it normal? Can I open the lib file? It was like,
It's a huge file. Your text editor will be like, oh, choking, I have a 48 megabyte file. Frequently, yeah. Yeah, it's a big file. And again, that lib file is only for one process corner too, right? You're going to have 12 of those. So when we start doing these designs, you start having like managing data and design data and library data becomes a problem. That's why you might only have a 6x6 cell instead of 8x8, because 8x8 is going to be 30% more file size. So.
the 6x6 like the number of like values it has?
Yeah, the 6x6 would be the number of input slews you characterize with and the number of output loads. So you just have a set of 6 input slews and 6 output loads. What are those 6 values? Those are generally going to be shared among all of your cells. And if you look at the prelogue, again, you have the units of stuff. There will also be something for like what those slews are. It'll have like a template lookup. And it will give you the values, as well as the units. Is this in nanoseconds or is it in picoseconds? What is it? And then what are the values? It'll list them out. Yeah.
Is it possible for a output slew to be more vertical than its input slew?
Yes, an output slew can be sharper than its input slew. Absolutely. Yeah, if that didn't happen, you could never fix a slew violation. So, yeah. Actually, I'll comment also. You can have some weird behaviors. Let me don't want to talk about it here. Maybe I'll talk about it later. I'm going to talk about it later. I'm way behind, actually. Yeah. Interpolating, just linear interpolation. So it's if you look at one dimension, let's say we have slew 1 and slew 2, and let's do concrete values. Let's say 1.0 and 3.0, and I want to know the value for 2.0. Well, what is it? Well, I take this value for 1.0, this value for 2.0, and I draw a line. I figure out this, right? But you're doing that in 2 dimensions now. So it's just instead of a line, it's a plane. Yeah, I'm going to keep that here. I need to get to the next lecture. I'll probably have a catch-up lecture soon. By the way, sprinkled in here, your midterm is only through homework 3. So actually, this stuff is not yet. I'm trying to think. I don't think anything on this is on your midterm. Is there any chance it won't be on there? Oh, I'll only do it if I forget, maybe. But no, I don't think any of this is on the midterm. I was just working on it yesterday, so I'm positive none of this is on the midterm. But this is honestly some of the most practical stuff we get out of this class, and you're going to use it in homework 6 and 7 a bit. And you're going to use this on homework 2. Actually, no, that's incorrect. Homework 3 has problems exactly on this. It has you looking up the lib file. So I take it back completely what I said. This is fair game on your midterm. Yeah, this is fair game. Now, yeah, complete 180, right? Not on your midterm, it's totally on your midterm. Okay, now what about the output pins? Again, here's an output, and you're going to have the function. Here's an A1 and B1, for example. This would be a NAND gate. There's a bar here. This is a prime in here that you can't see. The syntax, so it's A time and B1 invert. Again, I'll remove that so you can see. So there's a double quote and a single quote. Nasty, I know. Now, DFFs even are similar. Here, though, you have data pins, clock pins, and so on. And you can also have things like this that say, here's the transition function of when you store inputs and outputs and the state. Right? It's clocked on the clock 2 pin, and there's a reset called RST3, and so on. But they're very, very similar. Now, when you have these tables, where do they go? Well, you're going to have tables in here for pin A1. You're going to have tables here for pin B1 for all the different slews and output loads. Why is the output here? There's generally not any tables for the output pin. I forget what it does if you have multiple output pins. So if you have, say, output and output bar on the same gate, I don't remember the syntax to do that, but you can do it, for example. And here's in the prelogue at the very top, here's the example of how to find what the tables are. So for the delay table, for example, you can see this right here. Our library uses a 4x3 table, so much smaller than 6x6. And you can see one input here, the first index is the total output net capacitance, variable 1. values of 5, 20, 60, 200. What are those? I think it's femtofarads. I forget, but that's going to be defined in the prelog. And then you have the input net transition as the second one.
Is it actually misspelled in the files?
Oh, no. Actually, that's crazy. It could be. I'm pretty sure I cut and pasted this. This is not a keyword. It's something you define. So they could have made a typo. That's a good question. This is from the Sky 130 library. So yeah, it's not a keyword. It's you define it. And I don't even know where else you get it. You use it. I think it might even just be for a mnemonic. So I wouldn't be surprised if there's an error. You don't usually run spell check on these, right? So yeah, and so you can basically see this. And then here's an example actually of a delay. Actually, maybe the output pins are grouped in with the input pins. I forget. But here you see an example of the delay of an output pin, but it's not specifying what input pin it's coming from. And so, I'm confusing myself here about this. Because down here you see the rising table and the falling table for this gate. And what is going on here? Okay, so I misspoke before. The tables are not in here. They're actually grouped. Those are just the input pins. And then with every output pin, you have a kind of a set of tables, and you have this thing that says what the related pin is. So this is what I mean by, I don't expect you to know the format, but you can kind of get what's going on here. And so this is for this output O and the input pin A transitioning, and all the other pins are going to be held to some constant value, which is either the best case or the worst case for that gate. And we talked about finding the delay through logic gates. If you have, say, two parallel gates, two parallel transistors to find the worst delay, you want to not have both of them on, so that you have just the weakest one on. So you have a related pin, and then it's going to have some set of input conditions to have that input propagate to the output O. And then these are the tables here. So you have rise tables, fall tables, and you have them for different inputs, A1 and B1 and so on. And I'm not sure where this table's hanging out there. I forgot. I cut and pasted some stuff, and I removed some things. There's extra closing brackets that were never opened, so it's not a complete file. Yeah.
What is the difference between cell fall and fall transition?
Yeah, so cell fall that's a good question. This is the falling delay. This is the rising delay. This is and then this right here is the slew, the rising transition, the 10 to 90, the 90 to 10. Right? So I said you have those two tables for each input. So they call it cell rise and cell fall and rise transition and fall transition. Yeah, good clarification. Yeah.
What's the difference between like the rise delay, fall delay, and the slew?
This is the slew. The rise transition is the rising slew.
Oh.
Right? Remember, there's multiple ways you can say it. Rising transition, rise slew, the low to high transition. Yeah. Yeah, okay.
And then the time is presumably the female transition?
This depends, the time depends on the units. Before this, you'd see something. And I think that Skywater is in nanoseconds, if I remember correctly. I'm not positive, though. And then people are using GF180 in the capstone class. That has different units, too. Like, there's not standards. I'm going to kind of skip over. You'll have similar things for the setup times and the fall times. So, like, here is just an example of a setup time for a falling input. If your D pin, the input signal to your D pin is falling, this is how much setup time you need. Where if your D pin is rising, you're going to have a different table because those values change, and so on. So I've rarely looked at the flip-flop ones, but they have similar syntax and similar tables, is the point. Yes?
Wait, can you clarify what you mean by these constraints for setup?
I'm going to revisit setup and hold times, but you basically, if you have a signal transitioning differently, if it's rising, it's going to have a different setup time than if it's falling, because the different directions can have different characteristics in the gate. Yeah. And then these values also depend on not only the transition, but the slew rate. What does your D look like as it's going to the input of your flip-flop? What is the output load of your flip-flop? That can also affect your transition. But actually, it uses it's actually the clock also affects it. If you have a sharp clock, that will change your setup and hold time, or a very slow transitioning clock. So the point being, there's a bunch of different inputs that change these values. They're not just simple constants. Okay, I kind of showed some examples. I didn't get rid of this because this is actually part of your homework to do this. You're going to actually go through and look at some particular examples I asked you to look at for the homework and come up with the values. So, and you're free to talk about this and ask questions if you get stuck. But you should have enough info from what I showed there to see the values. Okay. Now, let's take like a 5-minute break. Okay. Let's get back at 22.
Actually, sorry, problem one. And I was actually
I have to get started. Yeah, I can answer questions at the end. So, all right, everybody. Okay. So I will confidently say that this material is not on your midterm. So yeah, but it is on the next midterm. So yeah. Now, why? So now we talked about capacitances. The one thing I didn't talk about is the wire part. So I only really talked about the fan outs, and I said, oh, there is wire capacitance. They add the delay. In fact, in many cases, they can actually add the delay more than the actual gates themselves. So we're going to talk a little bit about that. We're going to talk about a thing called coupling capacitance. So there's actually capacitances between wires themselves. If you have two wires next to each other, that can add capacitance. We're going to talk a little bit about interconnect variation. So we talked about the lib files just a minute ago with the different corners. Well, now you have the different corners for the lib files for the gates, but then we also have variation of the wires too. And so this causes this huge problem of how do you verify timing of these things, which is really the big challenge in chip design. Now, what's happening? So some of these plots are old, but the points still stand. And the thing we've seen over many generations over the last couple decades is that our technology is somewhere around here. In the capstone class, we're using this technology, 180. So these actually relate to what we're using. But if we think about it, when we're doing modern designs, we're doing 0.00, maybe 2, right? So just think about how much different this is there. And what we're trying to say is that each of these technology generations, the transistors tend to get faster. They get smaller. You scale things down, they get quicker. The problem is wires actually are getting slower. And so what happens is at some point, around 0.25 micron, 250 nanometer, wires dominated the delay of circuits. So they're about equal there, sorry. But then now wires dominate. And what this means is you can't just look at the logic cells. That has less of an effect on the delay than actually the wires themselves. And you have to include the wires before you really know the performance. Now, this used to be cool because back in the day, you could just say, oh, minimize logic levels. I'm going to have a fast circuit. That's not the case. Now, there's a lot of stuff built into this because not all what do I mean by a wire, first of all? Is it a short wire, a long wire? What do I mean by wire? Well, there's many different types of wires on a chip. If you see here, this is that crossover point when wires were roughly equal to delays of gates. Okay, 0.25. This is also a diagram I think from one of the books that I suggested you read. But what we see here is that generally there's different types of wires. So this left thing is again a side profile view of a chip. We've done that a lot for transistors. Where you have the poly gate, and the well, and the diffusion area, and the implants, and all that stuff. So down here you can see this is poly for a gate, right? Polysilicon. Well, right here is what we like to call local metal layers. It may be metal 1, metal 2 here, but we also have one called Li, local interconnect, right? So this may be Li, M1, you have different names. But the point being, the pitch of these, what I mean by the pitch, the width, oops, wrong one. The width in the x dimension is roughly the same as poly. They're on the same order of magnitude as poly. If you think about it, that's necessary because when you make a logic gate, you have all these poly gates, you need to connect the sources and drains, so you need the wires to be of the same scale to be able to route that cell. So you need a fine pitch. But the problem with this is if you look, so these are all wires going into the board, so it's the cross section. Whereas in real practice, you're going to alternate directions, so this layer would probably be going horizontal. But what happens is the area of this in the cross section is going to be related to the resistance. Those wires end up being very high resistance, and so you don't want to route them for very far. You want to keep them short. What you end up doing then is here we end up having intermediate metals, and here you end up having global metals. And what we see is that as you go up in metal layers, a couple things happen. As a designer, you can see that the width of these metals, this is the minimum width, gets wider. That's almost twice as wide as, metal 3 is almost twice as wide when it's minimum as metal 1 and 2. It's also taller. As a designer, you don't see this dimension, you don't see the height, because it depends how thick the metal is they deposit on it and etch off the other parts. So you don't see the thickness when you do layout. But the effect is that the cross-section becomes bigger. And they do that to basically make it lower resistance so that you can have longer wires with less resistance. And then at the chip level, the top global level of the chip, you end up having these big fat wires that are also tall to route everywhere. So you end up routing like your power supply in these top levels to carry a lot of current and have low resistance. Yeah.
Why don't they make like M1 and M2 taller?
Why don't they make M1 and M2 taller? It gets hard to process, and it's also hard to keep them that fine pitch then. So, because remember I talked about like chemical mechanical polishing and stuff? That step has an effect on how fine you can print these things. Yeah. Yeah.
You're saying local interconnect has the same width as the source? Like,
The local interconnects have a width similar to poly. It's not, poly's a little narrower, but it's similar.
like I don't understand why it has to be, it can't be like less than the...
You can't make it less because you can't print it. So this is as little as you can print. You can't print anything less than poly, essentially.
Okay.
And so you can make this the same as poly or bigger. And you don't want to make it bigger because then like you couldn't route it to make connection to say both the source and drain of the transistor. If you have a big fat wire, you have to be able to connect to both of them. So if it's too fat, you can't. And just also the number of cells, the number of wires you can fit in a cell to connect other things together, right? Remember, we go back to that previous slide when I showed like the left file and the inside cell routing. It's full of metal 1 usually. It's completely full of metal 1 in the cell. In general, we try not to use metal 2 at all inside of the cell. We reserve that for signal routing between cells at the next level up. And so if you make the metal 1 too big, you either have to space out the transistors to be able to connect them, which is then waste area. Now, what we've seen over generations though is, back in the older technologies, so this is probably 10 years before this 0.25 micron, you only had 3 metal layers, metal 1, 2, 3. And they were all about the same. So this is the width rule, and then the spacing rule on the right. But what happened is, as they added more and more layers, you can now use more layers to connect things. So in one way, design gets a little bit easier. But the problem is, you then have to start worrying about all this different resistance and different performance. And so now we're actually up to about 12 to 14 metal layers in most processes. The bottom 3 or 4 metal layers are going to be local. The middle ones are going to be these intermediate, and then the top few are going to be global interconnects. And then the idea is you reserve those for certain things, right? These local interconnects are either going to be routing inside of a cell or maybe inside of blocks. These intermediate wires are going to be routing together blocks. Maybe your ALU and your register file. And then the global things are going to be routing, say, from your memory bus all the way across your chip to your load store unit and your power distribution. So you end up kind of doing this functional reservation of these layers for particular cases. Yeah. That's an interesting question. What about diagonal layers? There was a thing in kind of the 90s where Cadence introduced it. It was called the X initiative. If you think about it, if you want to route 2 points, in this case you have to do 2 different layers, a vertical layer and a horizontal layer. Well, the shortest distance between 2 lines or 2 points is a straight line, right? So why not have a 45 degree? They tried it. The problem is that, first of all, the DRC checking becomes an issue. It's harder. You now think about what does the endpoint, you end up having a via at the end, and now you have a wire that has to enclose it like this. What is the design rule that looks like that checks that? It's kind of nasty. Or you have to rotate your via, right? But actually printing it's not a problem, so you can just rotate the mask. You can print it. But you end up DRC checking is an issue. They did get better wire length and lower capacitance, but the question was, is it really worth it with the complexity of the router and the DRC checking? And I haven't seen it since the 90s. Yeah, that's an interesting observation though. So let's talk a little bit about the types of parasitics of these wires. We're going to talk about the capacitance resistance. Those are the most important ones. Once you get to very high frequencies, inductance becomes an issue. Once you go off chip, say through like C4 connections through the substrate and stuff, inductance also matters. But for this class, we don't really think about inductance too much. That's going to be more if you take the ECE, was it 171 or 170 high-speed signal design, 173, that class. We'll talk more about inductance and stuff like that. We're going to talk about how they affect propagation delay. We're going to talk a little bit about power and a little bit about reliability too. Now, it's actually not so complicated to get an intuitive view of this. Now, think about if I have a wire. So this is a big fat wire on the right, right? It's a square. A square is a wire in an extreme case, right? A square of wire of metal is going to have a resistance associated with it. Now, there's two relationships. What if I make the wire longer? Let's say I take a wire and I double the length. What happens to the resistance of the wire? Increases. By how much? Doubles. Double the length, double the resistance. Perfect. What happens if I make my wire twice as in diameter, cross-section? Halves the resistance. It's essentially like you have two wires in parallel, right, together. Those are the two rules. So the total resistance of the wire, our wire, is going to be equal to a multiplier here called R square times the length divided by the width. So if we double the length, we double the wire resistance. If we double the width, we have the wire resistance. What is this R square? Well, if L and W are equal, what is that ratio? 1. So it is the resistance of any square. I can have a square that size, I can have a square that size, I can have a square that size. They all have the same resistance. Why is that? Well, the resistance is related to the height. We're looking at the width in this dimension and the length in this dimension. The height is always fixed. You don't control it. All the wires in a given layer have the same height. So this is related to the height. Another term for this is often called the sheet resistance. Okay, and so any given a plane, any sheet of that wire that's square is going to have the same resistance. Now, if you want, you then need to know that for every layer, what is the R square, or the sheet resistance, and then you can figure out the resistance of any wire. Now, funny story, and I'll say this. It's funny from my perspective, but it's unfortunate. Someone on the exam will always ask me R square. My exam printed incorrectly, right? That looks like a missing emoji. What goes in the square? It's a square. It's physically a square. And so every year, someone will ask me that's not here, obviously, and they'll be like, "Oh, my exam didn't print correctly." And last year, I remember I made a comment like, and they were like, in the review, they're like, "The professor made fun of me when I had a misprinted exam." And I'm like, "Can I tell you all this?" And then they were obviously not there, and I'm not going to tell you what that is on the exam. Okay, I'm not, because it's part of the definition. So that's important. It's the entire concept of a square, right? If you weren't here and you didn't listen, you will remember that if you're here. I guarantee everyone in this room will remember that. It's someone that's not going to listen to the lecture that is going to ask you that. And I'm going to try not to smirk at them this year. But, yeah, I just have to stoically say I can't answer that question. So, yeah, so any resistance, any square has the same resistance. Well, let me do another case. I can't easily add a slide. Actually, can I? I've actually never tried to insert a slide. Okay, let me do this instead. I'm just going to erase this, and let me look at, actually, we have an example coming up. No, I don't. That's good. So let's say we have some metal like this. Let's say this is a wire. It's going from here. Here's a via. Here's a via. What's the resistance of this wire in terms of R square? Let me draw it a little bit better to be, so it's actually rectangular. Well, what I can do is I can make squares. There's 1 square, 2 square, 3, 4, 5, 6, 7. This is 7 squares. What is the resistance? 7 R square. Doesn't matter what R square is. I know it's 7, right? Is it 8? Did I miscount? 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, 8 squares. Yeah.
So since the pins and interconnects are sort of offset from the edge of the wire, where do we start counting from?
Yeah, where do you start? The short answer is what if there's a via here in the middle? Where do you start counting? You start counting in the middle, the end. It doesn't matter that much. An 8 square wire is actually really short. When we start talking about resistance that matters, we're talking about like 100, 1,000. That half distance doesn't matter. So yeah, that's a good question though. The other question is, what about extreme cases? Like what if I have a bend like this? It's all in the same layer. This is supposed to be the same width, like an L. What would I do with the corner here? Here, you can actually count that as half a square. Because you kind of go around. Because if you think about the current flowing around it, it's not going to go flow all in one direction like this. Half of it's going to go around kind of the corner, inside corner. Half of it's going to go around the outside corner. So that's about half. But again, does it matter much? Probably not. In general, though, what will happen with something like this? They'll generally be on different layers. You'll have the vertical layer and the horizontal layer. You would treat those separately then. So, but yeah, that's the question here. Do you ever vary the width of a wire? That's a perfect question for right now. What happens if I change the wire? And let's say I have this red wire. Oh man, where'd my colors go again? Oh, I double tapped the thing and it comes back. Let's say this was on like Li. What if my layer is this instead, which is wider? What is the resistance of this? Well, 1 square, 2 squares. Let's say it's roughly 3 there. Let's assume those are evenly spaced. Well, this is now 4 squares, 4 R square, right? Because what happened? I made it wider, which meant the square got bigger, and so I needed fewer squares. And so making a wider wire makes the wire have less resistance, right? So you're going like this. You can't change the height. This is the layout I'm drawing from the top down. Okay, that's not this view from the side. So you can't change the height. That's the fab. They fixed it. This height, what I'm assuming, is say like 1.5 times this height here, which is 1. So you can make a wire wider. And I'm saying that this direction is the width, and this direction here is the length of the wire. So you can make a wire wider. And if you double the width of the wire, what happens to the resistance? goes down by half because of this formula down here, right? If I double the width, resistance goes in half. Yeah.
No, I meant like along the wires, on how
We have a secret person here that's an exam question I asked in a prior year too. What happens if I have a case like this, and this? What do you think? Depends how many squares there are. So what do you do? Kind of. I agree with that. And to be fair, when I did ask this question, I said state your assumptions. So I agree that kind of in this region, it's a little weird. But at a high level, what if I just divide this into squares and say, okay, that's 4. Maybe this is, say, 4 also. So you could do this in parts, right? You could say, okay, this is 4r squared. This is what 4r squared. Yeah. Yeah, they have the same resistance. I have a lot of people going, wait, what? No, they have the same resistance. Because remember, in the second one, it's wider, but it's also longer. I didn't draw it quite in proportion. Because remember, this square is bigger than this square. So it's bigger in the horizontal direction as well as the width direction. Yeah, that's my poor drawing, right?
Because they just cancel out because they're proportional.
Yeah, they're proportional. It's proportional. Your width and length of the square are proportional, and so they always cancel out. And you have this rule here. So the answer is that has the same resistance as the r squared in red over there. Exactly the same. Now, it's a little bit different because it's technically 2 resistances in series, but I haven't talked about anything about capacitance. If there's any capacitance along this way, you're going to get a different delay, right? So if you just look at purely at resistance, it's the same resistance. That gets us to the next segment. I'll talk about capacitance coming up. Now, what do the sheet resistances of different material look like? So I have 2 cases in here. It's kind of small print, so I'll zoom in. This is the old 0.25 micron text. You can see here's the different layers. So we have diffusion layer for the well, the N or P well. That has a sheet resistance, or R square. This says ohms per square. But I'll put it here again. This is R square. And it's in units ohms per square. So the well, that say N well that your PMOS transistors are in, it has a resistance of about a kilo ohm per square. What if I look at aluminum, the other extreme, the wires? That has a resistance of about 0.05 ohms per square. So that's a factor of like, what is that, like 10,000 difference, right? This well diffusion is a conductor, but it's a 10,000x worse wire than aluminum. So it's a bad wire. Poly, or this diffusion for the source and drain on the sides of the transistor, it's about 100x better than the diffusion because it's N+. Remember, the plus, that means you have extra electrons or holes, so it becomes more conductive then. So if you dope it more and make it more of silicon's a semiconductor, it can be either conductor or not. If you dope it more, it becomes more of a conductor. So adding more of that makes it. What do I mean by this with a silicide? A silicide is just a fancy way, you can see it down here with polysilicon too. Let me just skip the poly first. Polysilicon has a resistance of about 150 to 200, similar to the source and drain diffusion. But if we take both of these and we put a silicide on it, a silicide is essentially a thin layer of either a nitride material, which is more conductive than the poly or the diffusion. So you make a sandwich with something that's more conductive to make it less resistive. But usually you can control whether you want the silicide on the poly or not. You know, sometimes you might want it, sometimes you might not. Why do you think you might not want a silicide on poly? Who's taking analog design? No? When do you want to have something be resistive? If you're trying to make a resistor. How do they make resistors? Well, you make them out of diffusion or poly. So if I want to make a resistor, a 1 kilo ohm resistor, how do I do that? Here's an example of a question I could ask on the exam. Let's say you can only use diffusion. How do you make a 1 kilo, draw the layout of a 1 kilo ohm resistor? What's it look like? 1 square, yeah, exactly. This is the type of thing, you have the ideas, you can apply them to the next concept, and I can ask you a question in the reverse, you use the same principle to come up with a solution. Or how do you do a 1 kilo ohm polysilicon resistor? Well, if you assume it's 150, let me say 1.5 kilo ohm. Well, you need 10 squares. 10 squares in a row. There you go, done. So yeah, so that's exactly the type of thing. What does it look like for a newer process? So here's the SkyWater info. By the way, the nice thing about all this open source stuff is all this stuff was proprietary until they open source SkyWater. We had to rely on the old stuff from 30 years ago in the book because I couldn't tell people, I couldn't put it in slides and put it online. Yeah.
Can you explain that concept about like how many squares to make it whatever resistor?
Yeah, all I did was I took this equation. I said, I want 1.5 kilo ohm. It's in diffusion, which has a R square of 1,000. What size do I make it? Well, 1,000 equals 1,000 times 1. Or if you do the poly, this was 1.5 kilo ohm, this was 150. What constant equals that? Well, 10. So just same equation. This class is all linear equations in any direction, right? Elmore delay, this, linear equations everywhere. Yeah, that's a good question, though. It's always good to state things in multiple different ways because people get it when you approach it from a different perspective. What does it look like for SkyWater? So I mentioned that book was the old 0.25 micron, SkyWater's 0.13. I can't really tell you what this stuff is from newer processes because it's secret, right? You have to sign an NDA before you know it. Why do they care? Well, you can start to tell how thick things are. If you know how thick things are, you can start to reverse engineer their processing steps. So generally, they won't even tell you how thick things are. It's a secret, right? So, because that's all the secret sauce to make the chips. But the interesting thing is, so first note that this is milliohms up here. So it's not ohms, it's milliohms. So technically, this is 48.2 ohms per square, which what was poly over here? It was 150 to 200. Same ballpark, right? 3x difference, but similar. I don't know if that's poly with the silicide or not. I don't know. What about local interconnect? That's 12.8 ohms per square. Metal 1, that'll be 0.125 ohms per square. Again, that's similar, right? That's pretty close. But this Li is actually about 10x worse than the aluminum or the metal wires. So again, Li is, I think it's mostly made out of tungsten because it's more malleable and they can kind of print it a little finer. And so it's a little more resistive than the aluminum. Yeah, but it has a finer pitch than metal 1, I believe. And then you can see as you go up, you can start to see our stack. Here, actually, I would categorize these, and this. Here's our local wires. Here's our intermediate wires. And here's our global wire. Right? You can see the resistance. It goes down by basically half an order of magnitude each case, which means we're basically, the height goes up by about 50% or something like that.
In SkyWater, metal 5 go both horizontally and vertically.
So technically, any layer can go vertically or horizontally, but by convention, you're going to want to stick to one to make it easier to route. Because if you go one direction, you block every wire going the other direction in an entire layer. So if you coordinate among all your layers, you can route more efficiently. That's the short answer. The long answer is Metal 5 ends up being that redistribution layer that you can like do things. Actually, no, redistribution is another layer. It ends up being mostly power, and so I think it is primarily on one layer, but they allow it on some other directions. Now, that's another answer, which is a wishy-washy answer. The third answer is that when you get to real tools, they don't exclusively say you have to be in one direction. What they'll generally do is they'll add preferences in your routing tool and say, here's the cost of routing a layer. Say 1, 2, 3, 4, 5. They'll have what's called a non-preferred direction cost, and you'll give it a constant in your config and say, I want to weigh something going in the wrong direction 5x more than something going in the preferred direction. And then what it will say is if I can make a connection and it's less than 5 links and I can do it in one link, I'll do it by going off direction. So it's like, what's the trade-off in your mind as a designer? You can configure it. But as you allow more and more off direction, the router complains more and more because it becomes a harder problem. Yes?
Just clarifying. So the resistance per square decreases from local, intermediate, to global because the width of the square is
The height of the metal goes up. Yeah, this prior thing I showed right here. The height goes up, which means this cross, and the width gets a little bit bigger. But in general, the cross-sectional area is bigger, which that is the r squared. Remember, the r squared is related to the width and the length, but the height determines it. You can think of it as a 3D equation to find the total area of the metal wire, right? Yeah.
In a given like layer, all vias are the same size, right?
In a given layer, all vias are the same size. Yes, but vias get bigger as you go up also.
But in a given layer.
Yeah.
So then you can know that via will have a constant amount of resistance.
Yeah, that's another good question. What about vias? Did I have that in here?
Yeah, that's what I'm seeing.
Yeah, down here. What are via resistances? That's a good observation here, and I wanted to kind of point that out. Well, a via here, if we again convert to the correct units, 4.5 ohms per square. But all vias are generally square, as you just said. Actually, this is actually a sheet resistance. It is, but you can't change the size of a via by the design rules. So they're always square, and so each via will have this resistance. But what can you do to change the resistance of a via? You can't change the width like you can a wire. Have more vias. We've seen that in some of the layout. If you have a diffusion, add 3 vias. If you have 3 vias in parallel, it's now 4.5 with a 4.5 with a 4.5 in parallel. It's much less than 4.5. So it reduces resistance, but it also is a reliability thing. If one of those vias fails and doesn't match through, you have 2 more. Yeah, you can see each of these two. And these are related to the height difference. If I go back to the metal stack, you can see these are roughly look like they're all about the same, but the height of this could be different than the height of this, right? The amount of oxide between the metal layers can actually be different. And why would you want it to be different? Well, that's going to be related to the next thing, the capacitance. So I'll get to the high level, and then we'll not get to the delay computation in this lecture. I'll start with that next time, but we'll be able to talk about the capacitance and call it quits. The nice thing here is we can use a simple parallel plate model. We basically already used this when we did, for example, the diffusion capacitance for like the source and drain, right? Except we had a parallel plate for the bottom of the source and drain, the sidewalls, and so on. Here now we basically have a couple things. Either you have interlayer or intralayer. So interlayer is shown here, where this top one might be metal 2, and this bottom one might be metal 1. And these are basically over each other, and you have capacitance between them. So if you have a square on the bottom and a square on the top, the formulas on the right, again, a linear equation, determine the parallel plate capacitance. There's 2 components. One is related to the area, so that's the CPP, C parallel plate, and it's a constant. What is that? If we view this as a capacitor, again, top layer, bottom layer like this, what was the equation for capacitance? It was C equals,
A epsilon over D.
yeah, it's A epsilon over thickness, like Tox. So Tox is dependent on the manufacturing. How far apart are these metal layers when you deposit them based on how much oxide you put before it? It's fixed. You don't control it. What is epsilon? Well, it's a silicon dioxide. It's a chemical. It has a property. You don't control it. You control area. So in this case, if we look into the top of this capacitor, we see the view over here, this top plate over a bottom plate. There's a length and width of that plate. So let's call it length and width. And that determines the parallel plate component of it. Now, in addition to this, so those are basically, if you look at a capacitor like this, those are the kind of direct field lines between the plates. We can also have fringe capacitance, which are basically the edges. And there's a field that kind of goes around the edges from one end to another end. And that is the second term there, the CFR, the fringe capacitance. And that is a component related to the perimeter of this thing. You can fringe between the top perimeter and the bottom perimeter. And so in this case, it's the perimeter here is 2L plus 2W. So again, linear equations, some simple geometry, and you can roughly estimate what that is. The problem is that when you have complex layout, it's not usually just a simple parallel plate with 2 equal-sized plates. So if we look in the case over here, on the left, this is the case from metal 1 to metal 2. What do we mention about directions of wires? Well, in general, the directions are going to be alternating. So most often, metal 1 will go this way, metal 2 will go this way. How much area overlaps on a given wire? Not a lot. Between 2 wires, there's only a little bit of overlap. Right? Let me draw, say, Let me draw some layout and say, oh, this is one layer. This is the other layer. Well, what's the capacitance between these? Well, it's related to this. Not much. What happens if I have many wires? Well, each of these will have a capacitance, right? So it's not one big capacitor, it's a bunch of parallel capacitors between different things. So it's a little bit complicated. That's for basically interlayer capacitance. But what is the capacitance between metal 1 and metal 1? Well, if I look here, I just drew these parallel blue lines. They go the same direction on the same layer for a long time. That means the parallel plate between the sides of the wire. So again, this thing on the right is the side view, and this is the height in the up dimension, right? This is between the same layer, between wires on the same layer. This is metal 1. So you can have capacitance there, and what is the distance between them? Well, it's probably the minimum spacing you can draw. You want to pack your wires in. So it's your design rule as a designer, it's your minimum spacing between the wires. What is the parallel plate size? Well, in this case, the length, one dimension is going to be the length of the wire. What's the other dimension? The thickness of the wire. For this is within one layer, it's the thickness. What does that look like? Let's go back here to the scaling diagram. What happened here? Look at this. These ones got taller. What does that mean? If let's say that these bottom ones got taller. Someone asked me, why don't you make those bottom wires taller? Here's another reason. If you make them taller, there's now more capacitance between those wires on the same layer. And you don't want that. So you keep them short so they have low capacitance between each other, and you can pack them in there. Now, the top ones, you made them taller to reduce the resistance, but you're also spreading them out. The spacing is more, so that's to reduce the capacitance. So you're trading off resistance and capacitance with these big fat wires. Yeah, so this shows kind of short wires, right? There's not a lot of capacitance between the things. Now, how has that scaled over time? And I'll keep this last slide. It's gotten worse over time. So if you look at a wire 90 nanometer, that's one generation newer than SkyWater. The height is about 2.5 times the width, the height of the wire. And so that coupling capacitance gets much worse. And so you see this trend with the design rules. Where are we at in this? We're 130 nanometer, 0.13. This is in microns. This is micron wire width. I forget the wire width in SkyWater. It's like, I don't remember the design rule. But anyways, the point being that this has the C ground is the capacitance to ground, and this is the wire to wire. Those two components. You can see that sometime after here, the oh, sorry, no, the C to ground is not it. The parallel plate is the one we want to talk about. This goes up linearly. And, oh, because we're scaling this way. This is a smaller technology, right? As we get a smaller technology, we go to the left. And the interwire, the wire to wire on the same layer goes up. Whereas the parallel plate capacitance, the area one, goes linearly down because we're decreasing the size of the wires, right? So you see it skyrocket right around there. Okay, that's all I'm going to cover today. So next time we have resistance and capacitance of wires. Now how do we do delay? We'll talk about that.